we immediately think of table salt, also called sodium chloride. This is a mineral that is essential for animal life and has many everyday uses as a widely used flavoring for food, as a method for preserving food, and even as a cleaner for removing stains. But there are many other salts besides sodium chloride. What they have in common is that all salts are formed when metal ions or the ammonium ion takes the place of the hydrogen ion or ions of an acid. For example, magnesium sulfate is a salt formed when the H+ ions in sulfuric acid are replaced by magnesium ions. Zinc chloride is formed when the hydrogen ions in hydrochloric acid are replaced by zinc ions. Salts can be classified in two different ways. Let's look at these ways. Firstly, as normal salts or acid salts. Normal salts are formed by the complete replacement of the hydrogen ions or protons of an acid. For example, sodium chloride and potassium sulfate are made by the complete replacement of all the hydrogen ions in hydrochloric and sulfuric acid by the sodium and potassium ions respectively. Acid salts are formed by the incomplete or partial substitution of the protons in acids with a basicity of 2 or higher. Sodium hydrogen sulfate and disodium hydrogen phosphate are examples of acid salts that are formed from sulfuric and phosphoric acids respectively. Another way to classify salts is as hydrated and anhydrous salts. Hydrated salts are salts formed with water of crystallization, while anhydrous salts have no water of crystallization. Given that the method of preparation chosen for a salt is primarily dependent on its solubility in water, it is important that the salt solubility rules are learned by all students. All salts, in actual fact the vast majority, containing the ions sodium, potassium, and ammonium are soluble. Nitrates. All nitrates are soluble. Metallic halides, chloride, bromide, iodide, all halides are soluble except silver and lead. Lead-2 chloride and lead-2 bromide are soluble in hot water. Sulfates. All sulfates are soluble except for barium sulfate and lead-2 sulfate. Calcium sulfate and silver sulfate are slightly soluble. Carbonates. All carbonates are insoluble except for sodium carbonate, potassium carbonate, and ammonium carbonate. Hydrogen carbonates. Most hydrogen carbonates are soluble. Salts can be prepared in several ways depending on whether the salt is soluble or insoluble in water. Soluble salts are prepared by neutralization or direct combination. Insoluble salts are prepared by This method is used to prepare soluble salts by the reaction between acid and base, including alkalis, acid and reactive metal, where the metal must be above hydrogen in the reactivity series, acid and carbonate, acid and hydrogen carbonate or bicarbonate, acid and base reactions. The acid and the base reaction produces a salt and water only. An example of this reaction is the reaction of potassium hydroxide, an alkali, and hydrochloric acid to produce potassium chloride and water. An acid can also react with an insoluble base to form salt and water only. An example of this is the reaction of sulfuric acid and zinc oxide. Acid and metal reactions. The action of acids on excess metal will yield salt and hydrogen gas. There are 3 considerations when choosing this method. 1. The metal has to be above hydrogen in the reactivity series. 2. Very reactive metals, such as potassium and sodium, react too violently with acid for the reaction to be easily controlled, so they are generally avoided. And 3. Metals which are just above hydrogen in the reactivity series, such as lead, will react too slowly for the reaction to be of any productive value. An example is a reaction of magnesium metal with sulfuric acid. The action of acid on carbonates and hydrogen carbonates. An acid reacts with a carbonate or bicarbonate to form a salt, carbon dioxide, and water. Examples of the reaction between carbonate, hydrogen carbonate, and acid are shown. Measuring cylinder. Measure a given volume of dilute acid into a 250 milliliter beaker. Place a small amount of the metal, base, or carbonate into the acid and stir. Continue to incrementally add the solid reactant to the acid while stirring until all the evidence of the reaction ceases, that is, effervescence stops, and excess metal, base, or carbonate starts to accumulate on the bottom of the beaker. Warm the beaker and its contents on a Bunsen flame, and if the solid reactant on the bottom of the beaker reacts and disappears, add more solid reactant while stirring until it starts to accumulate on the bottom of the beaker again. Remove the beaker from the heat and allow it to stand, thereby allowing the mixture to cool and the insoluble components to settle on the bottom of the beaker. Flute the filter paper and assemble apparatus to filter the mixture into 250 milliliter earth and reserve the filtrate. Place the filtrate in an evaporating dish and slowly heat the mixture on a low Bunsen flame, hot plate, or water bath until crystals start to form on the edge of the surface of the mixture. At this point, dip a clean, cool glass rod into the mixture and immediately remove. If crystals are seen on the glass rod, remove the evaporating dish from the heat. Cover the evaporating dish with perforated filter paper and leave in secure position on a laboratory bench for a few days. Dry crystals with blotting paper and store. By adding the solid reactant in excess and then filtering off the excess, one is making sure that all the acid has reacted. In other words, the acid is made the limiting reagent, thereby ensuring that the filtrate is salt and water only. The salt is then crystallized from the aqueous mixture. This method normally produces hydrated salts. Usually, the salt can be made anhydrous by heating over time in a crucible, provided that the salt the acid in a 50 or 100 milliliter burette and take an initial reading. Using a pipette, place an aliquot, 25 or 50 milliliters, of the alkali or carbonate bicarbonate solution in a 250 milliliter Erlenmeyer flask or beaker. Add 1 to 2 drops of a suitable indicator to the solution in the Erlenmeyer flask. Run in the acid from the burette until the indicator just changes color and take a final reading. Determine the volume of acid dispensed from the burette by subtracting the initial reading from the final reading. Repeat the experiment without the indicator, using the same aliquot of alkali or carbonate by carbonate mixture, and run the exact volume of acid from the burette as before. Transfer the mixture from the Erlenmeyer flask to an evaporating dish and crystallize salt. Indicator's function was to signal the end of the reaction, that is, the point at which the alkali or carbonate mixture has completely reacted. In previous preparation, the end of the reaction was signaled by the insoluble reactant accumulating in the reaction flask to be easily removed by subsequent filtration. However, with soluble reactants, the end of the reaction would not be as obvious, and the resulting salt solution could easily be contaminated with excess alkaline carbonate, bicarbonate, or acid. The burette and pipette were used so that accurate volume measurement could be taken of the reactants, ensuring that neither reactant is in excess. Insoluble salts can be prepared by precipitation. This method involves mixing together the solutions of 2 soluble salts, where one salt contains the cation of interest and the other solution the anion of interest. Lead nitrate plus potassium iodide gives lead iodide and potassium nitrate. This method involves the reaction of 2 elements directly with each other and is generally used to prepare anhydrous-soluble or insoluble salts. Or if one element is a gas at room temperature, the dried gas is passed over the heated metal powder. This method can only be used to prepare binary salts, that is, salts containing 2 elements only, and is generally avoided where the elements react violently. For example, potassium chloride would not be prepared in the laboratory by reacting potassium metal with chlorine gas, as the ensuing reaction would be violent. Examples of salts that can be prepared by direct combination are iron 2 sulfide, occur in the Earth's crust in the form of ores. Ores are naturally occurring metallic compounds from which metals can be extracted. They are usually impure because of the contamination by other materials. Ores are usually oxides, carbonates, sulfides, or sometimes chlorides of the metals. Ores are ionic compounds where the metal is present in its cationic form. Extracting a metal from its ore involves the conversion of the metal ions to metal atoms by reduction. Reduction is the gain of electrons by the cation. For example, copper 2 plus 2 electrons gives copper. Zinc 2 plus 2 electrons gives zinc. In order for reduction to occur, there must be a source of electrons. These electrons can be provided by reducing agent or by the cathode during electrolysis. In the extraction of a metal from its ore, it has to be first mined. The ore is then purified before the reduction is carried out to remove unwanted rocks and minerals. Some ores, usually sulfides, are roasted in air to form the metal oxide. The metal that is produced is purified or refined to further remove impurities that it may contain. In some cases, it may be alloyed. There are several ways to extract a metal from its ore. Each method is based on the position of metals in the electrochemical or reactivity series. The reactivity series ranks metals in order of reducing power. The most powerful metal, that is, the most powerful reducing agent, is placed at the top of the series, and the least powerful is placed at the bottom of the series. Hydrogen is included in the series to show its reducing power relative to the metals it is often reacted with. This method is used where the ore is a compound of very reactive metals. Metals such as potassium, sodium, calcium, magnesium, and aluminum can be extracted from their purified ores by electrolytic reduction. Aluminium is one of the elements that is found abundantly in the Earth's crust, but it is never found in its elemental form. It occurs chemically bonded with other elements, mainly in the form of aluminosilicates. Alumina is extracted from one of the ores of aluminium, mainly bauxite, and the aluminium is obtained by electrolysis of the molten alumina. Pure alumina melts at 2050 degrees Celsius and is dissolved in molten cryolite in order that the mixture remains a liquid at a lower temperature of 950 degrees Celsius and the conducting properties of the melt improve. The mixture is electrolyzed in a steel tank between a graphite or titanium alloy anode and a graphite cathode that lines the tank. The molten aluminum settles at the bottom of the tank and is tapped off. At the cathode, liquid aluminium 3+ ions become liquid aluminium. At the anode, liquid oxide ions become oxygen gas plus 4 electrons. This method is suitable to extract metals that are below aluminium in the reactivity series of metals. Metals such as zinc, iron, and tin are moderately high in the reactivity series and can be extracted by this method. This chemical reduction can be done with carbon, carbon monoxide, or hydrogen because they are all reducing agents and are capable of reducing the oxides of metals below aluminium in the reactivity series to their respective metals. Carbon monoxide, being the most powerful reducing agent of the lot, is usually the reducing agent of choice. Ores that are metallic carbonates and sulfides are usually converted to the oxide by heating in a kiln and roasting in air respectively. Traditionally been produced in a blast furnace into which dried hot iron ore or impure oxides of iron, coke, jar impure carbon, and limestone are added from the top. Hot pressurized air at approximately 1900 degrees Celsius is blown into the furnace from below the raw materials. This causes the coke to burn, producing carbon dioxide and heat. At the high temperatures of the furnace, the limestone, which is a form of naturally occurring calcium carbonate, thermally decomposes to calcium oxide and carbon dioxide. The carbon dioxide produced by both reactions is reduced to carbon monoxide by the hot uncombusted coke. The hot iron oxides are then reduced to iron by the carbon monoxide, and the molten iron settles to the bottom of the furnace and is run off into shallow trays and allowed to cool. This iron, now known as cast or pig iron, is impure and is mostly used to make steel. The basic calcium oxide reacts with the primary impurity, silicon dioxide, which is silica or sand, to form calcium silicate, which forms a molten slag that settles to the bottom of the furnace and floats on the molten iron and is run off separately. Some processes of iron extraction employ mixtures of carbon monoxide and hydrogen to reduce the iron oxides. These involve other methods that have been used to extract metal from their ores. Metals below hydrogen in the reactivity series of metals generally fall into this category. For metals found native or uncombined in the soil, no chemical reduction is necessary, only washing and purifying. Metals which are sometimes found native include gold, silver, platinum, copper, mercury, lead, and chromium. These metals are all low in the reactivity series, hence unreactive. And so this brings us to the end of our lesson for today. Thank you for joining us.